Avogadro's number is a massive number, and this is a reflection of how small atoms actually are. 6.022 times 10 to the 23rd. For example, if you had that many popcorn kernels, it would cover the entire planet in 6 feet of popcorn. But if you had that many water molecules, it would be about an ounce of water. So, why is this number so important? What it is, not exactly, but kind of close, is that if you had this many protons, it would weigh 1 gram. And a gram is something that's measurable on a balance in a normal lab. Or if you had that many neutrons, it would weigh 1 gram. Of course, this isn't exactly right because the mass of a nucleus is also defined by the energy stored in it. This is what Einstein pontificated with E equals mc squared, where the energy released in a nuclear reaction is equal to the mass lost times the speed of light squared. But for our practical purposes, it's about right. 1 mole, Avogadro's number is also known as a mole, and 1 mole of protons is about 1 gram. What we really need to know is that 1 mole of carbon atoms is 12.01 grams. On average, a carbon atom is 12.01 atomic mass units. An atomic mass unit is a very, very, very small unit, and 1 atom of carbon is very, very, very small. All carbon atoms do not weigh the same. All carbon atoms have 6 protons. If it has 6 protons, it's carbon. If it's carbon, it has 6 protons. That's by definition. But it can have a different number of neutrons. There's carbon 12, which would have 6 protons and 6 neutrons. Carbon 13, which would have 6 protons and 7 neutrons. And carbon 14, which would have 6 protons and 8 neutrons. The average mass is 12.01 because almost all of carbon is carbon 12. By the time we get this many carbons, all we have is the average mass. Avogadro's number has units. It's like a dozen. You can say 1 dozen equals 12 things. I mean, you can even say a dozen things equals 12 things. And so 1 mole of things is this many things. And so this many things is equal to 1 mole of things. And really the things here that we're going to use this number for are either atoms or molecules. This turns out to be important because when we do basic math with a mole, if I told you I had 42 things and ask you how many dozen is that, well then you'd put the 42 over 1 in standard dimensional analysis. And again, this is units of things, and so I know I need things on the bottom, and I'm asked how many dozen, so I want dozens of things on the top. And so then I have to be a little thoughtful. There are 12 things in 1 dozen. And so in the end, things cancel. And when I put an equals here, I'm going to get 42 divided by 12 dozen things, which equals 3.5 dozen things. I can obviously do exact same thing with Avogadro's number. If I said something like I have 3.7 times 10 to the 25th atoms of, we'll say, carbon. And I ask, how many moles is that? Again, in chemistry, we use dimensional analysis as our format. You could do this as a ratio and cross-multiply and such, but that's not the way we do it in chemistry, and there's reasons for that, as we'll see as we move into stoichiometry. 3.7 times 10 to the 25th atoms of carbon divided by 1. Again, I'm going to multiply by a fraction, and on the bottom is going to be atoms of carbon. I already know that because I know atoms of carbon is going to cancel, and I ask myself how many moles, and not just moles, moles of carbon. So moles of carbon is going to go on the top, and then I can be thoughtful. There are 6.022 times 10 to the 23rd atoms in 1 mole. And so here I can do this math. I think it's nice to do the math with a calculator. There's 2 different ways of doing it. You can simply say 3.7 divided by, oops, better turn the calculator on first. 3.7 divided by 6.022, enter. And again, there's 2 significant figures here, 4 there. I can stick with the 2, so I only need the 6.1 here. And I get 6.1 times, oh, I have it in scientific notation, got to be careful. That's to the minus 1. This is 0.61, and again I could change that back by going into my function mode and changing it to normal and get my 0.61 times 10 to the 25th divided by 10 to the 3rd is 10 squared. Again, this would not be scientific notation because the decimal is in the wrong place. I would have to multiply this by 10 and divide this by 10, so it would be 6.1 times 10 to the 1, or 61. If I wanted to be more diligent with my calculator, I could do that differently by putting 3.7 E. I don't know why I didn't do that. Oh, that didn't work. Again, 3.7 E25 divided by 6.022 E23, and I'd get 61 as my answer to 2 significant figures. That is not a complete answer because it needs units. The units left over are moles of carbon. Moles of carbon. This makes sense because 1 mole is 10 to the 23rd. This is 10 to the 25th. I should certainly end up with a lot more than 1 mole, and about 61 moles does make sense.